Okay, I'm going to do my best to describe the electric drive system. We're going to start over here on the port side. On the port side, we'll do a little bit of component identification. These are basically the drive batteries. There are 2 individual batteries with 16 cells. These are the EVE 3.2 volt lithium iron phosphate battery cells that you can buy from AliExpress. That's where I bought them from. We have flexible bus bars. We have a spring pressure plate system that keeps the battery cells in constant compression, but will allow them to move back and forth if necessary. The neat thing about those particular springs, they are pretty strong to the extent that I can turn this box upside down and the batteries do not move. So there's no need for additional, a safety bar across the top to keep the batteries in place. The batteries literally are locked in place through compression. Each battery has its own 300 amp fuse coming off the positive battery post. So they're fused at the battery post. And then once they go past the disconnect relays, each individual circuit is then fused appropriately for that circuit. Protecting the battery, we have your standard 16 cell. It's actually 16 to 20, I think. (10 to 16) cell battery management system. This battery management is unique in the fact that it doesn't have MOSFETs. It doesn't use, like the DALI system, it doesn't use MOSFETs to disconnect the battery in a condition of being overcharged or an overcurrent condition. What these battery management systems, and there's one for each battery, they send a 48 volt signal to these relay clusters. When this relay, either of these relays for battery 1, battery 2, if they notice an anomaly, whether the battery voltage is too high or too low, they're going to send a signal to this time delay relay. The job of this time delay relay is to send a pulsed signal, so a momentary on signal to these battery relays, disconnect relays. So instead of having a MOSFET that opens the circuit, we now have a relay. These relays are also unique because they're not constantly energized. They're energized only with a momentary signal to either turn on or turn off, or to open or to close. So in the case of a fault, I'll duplicate a fault by just disconnecting this 48 volt signal. We're in alarm. My alarm panel shows that I have an alarm. Alarm's reset, but my disconnect switch is still open. And I have to come and check out what's going on inside the battery compartment. Why did the batteries fault? And if I think the condition is cleared and it's safe to turn the batteries back on, I can manually turn the batteries back on. What's nice about this is that I can also manually turn the batteries off. Now they're locked out. I can do maintenance, and there's no way that someone from another panel somewhere could turn the batteries on, or that they could accidentally be reconnected. There's just no way to turn it back on. When I'm ready to put the system back into service, I can turn it back on. I can either hit the switch back at the control panel to turn the relay back on, or I can manually turn it back on. If we were to lose power to the battery management system, if this entire battery management system was to fail for whatever reason, and it was non-functional, and our relays disconnected, we would need the ability to limp back home on the batteries. So again, one of the pluses is I can just come over here and manually turn this relay on. It is electronically controlled, but it also has manual controls that allow me to go back into limp mode and get back to where I need to go safely under electric power. So that's the basic BMS. I have not found a good location for the little display panels, but they're pretty cool. You get to see the voltage in each of the cells, and you can see that they're balancing pretty well. every cell is at 3.29 exactly. On battery 1, let's see, battery 2 is at 3.29 exactly. It just doesn't get much better than that. I didn't do anything special to do that. I basically hooked up the BMS and it took care of that by itself after some top balancing. Does this go back on? I don't know. There. Just to keep me from sticking my fingers in there or dropping the tool, because it is pretty scary. I didn't mention this, but these flexible bus bars, also from AliExpress, are really cool. They allow the batteries to grow or to shrink and grow. And this little bend in here is super flexible if I was to take them out. And I thought it was pretty important for the batteries to be able to move without interfering with these terminals, because they're not very big. They're 6 millimeters each. I didn't want to take a chance on shearing one of those off or having a bad connection. So first time I'm using these, I'm very, very excited about them. They seem to do the job. Okay, so that's the batteries in a nutshell and the battery control system. From the batteries, we have basically two 48-volt battery outputs going to a common bus bar. The common bus bar sends power to the starboard motor, the port motor, the inverter charger 1, and inverter charger 2. This is our port motor system. From here, we have a standard contactor that comes with the kit for the electric motor, the Sevcon Gen4 motor controller that comes with the kit, little communication box for all of my harnesses, including the throttle and the gauge, and then the motor itself, which is an ME1904 Motenergy electric motor. This is not the sealed version. They have a sealed version. They also have a liquid-cooled version. Both of those are very nice motors. This is the motor we have. I can explain why, but my point would be we had a motor very similar to this in our last electric boat. It functioned quite well. So for the cost and for the simplicity of the system, we chose this motor. If it does fail because of corrosion or the marine environment or something like that, we will simply unbolt it and buy a new one. So we get a signal from the throttle. The motor controller is basically taking 48 volts, converting it so that the motor knows which way to turn and how fast to turn. This plate is from Thunderstruck EV. They actually provided the entire motor and controller assembly for my last boat, but just the plate for this assembly and the reduction gear. This reduction gear allows us to spin the shaft slower than the motor. The motor is very happy to go 4,000 RPM. The shaft is not. So the reduction is very similar to the Kanzaki transmission that used to be here attached to the Yanmar originally that came with this boat. It's 2.67 to 1. So for every one rotation of the prop shaft, the motor rotates 2.67 times. We're basically bolted down to the original stringers where the engine was, which puts the motor assembly plate at just the right angle to meet up with the existing prop shaft. And yeah, it's a pretty simple install. If we didn't need to put the batteries in here or other accessories, it would be very, very clean in here. But even with the electronics we have, it seems like there's room to move around, and it's not quite as packed or as busy as it was when there was a big diesel greasy engine in here. I much prefer the electric motor. It just stays clean. So that's basically how we drive the prop shaft. In order to charge these batteries, we've installed two EG4 3000 watt inverter chargers. The inverter feature is a little bit of overkill. So one of these inverter chargers is enough to power the boat. We will not run both at the same time. In fact, we'll only be able to run one. And then if we want to select the other, we can select the other, but never both at the same time. They're not run in parallel, and the system's not designed to do that. Honestly, because I just wanted to make the boat simpler, and I did not want to have, 6,000 watts available to me, because once you have 6,000 watts available, you use 6,000 watts. And I wanted to keep the boat as energy efficient as possible. So what these are good for is the charger part of the inverter charger package. So each one of these has a capacity of 60 amps charging at 60 volts. So that's a considerable amount of charging, 120 amps going into the batteries if I needed it. However, the generator can only, it's a 7 kilowatt generator, and we really only want to pull about 6,000 watts. So essentially at sea, when we're motoring and running the generator, we'll be setting these up so that each of these will be putting 50 amps back into the batteries. So that's 100 amps total. If we are motoring with the generator on, my assumption is that we're going to be burning about 50 amps on propulsion and sending 50 amps into the batteries. Best case scenario. But if we need to be using 80 amps on the batteries or on the motors in order to, achieve a reasonable speed, we still will have 20 amps going into the batteries. We'll still be net positive. We'll still be charging the batteries. And that's what the generator is designed to do. It's there to charge the batteries, and it's a range extender, because looking at these batteries, we have, a maximum of about 14 kilowatts maybe per battery. Even if you just conservatively said we could get 20 kilowatts out of these at 50 amps, that's 10 hours of motoring. So 10 hours, after 10 hours of motoring, I'm done motoring. I don't know if the boat can go longer than that, but I certainly don't want to. That's not what this boat is designed to do. So in theory, we'd probably run 4 hours on the batteries, run the generator with the inverter chargers for 4 hours, and then alternate back to straight battery power, giving the generator time to rest in between. This isolation transformer is hooked directly to our shore power plug. So when we do get power from the docks, it's going to go to this isolation transformer and completely be disconnected from the rest of the boat. This isolation transformer creates its own ground, creates its own neutral, and sends the one leg of 30 amp power over to one of the inverter chargers. I don't have it hooked up to both. I can hook up to one or the other, but not both. So I have redundancy, but I'm not blowing the breaker on the docks and upsetting, the dock master, because I'm pulling 60 amps, which seems like a little bit more than any one yacht needs to be pulling at a time. I'll pull 20 to 25 amps, charging the batteries at a slow rate. And if I'm hooked up for the night, I can charge overnight. I can charge all night long, which is more than enough time to if I come in basically limping on a dead battery, I'll still be charged by morning. There's no sense in trying to charge at 100 amps unless I'm running the motors. Anything else on the port side over here? I think that's about it. Hopefully it seems simple. I know, I don't necessarily go into what's going on inside each of the pieces of equipment. I just know what they are and what they do, and that they work.